Welcome to the Python Programming Tutorial Series for Climate Mathematics Theory and Applications, Chapter 5, Energy Balance Models for Climate Science. In this video, we will compute EBM for modeling the moon's surface temperature. Also, examine nonlinear albedo feedbacks for global average surface temperatures. Let's begin by importing all of the necessary packages and libraries to compute the energy balance models for climate science. Section 5.1 in the Climate Mathematics book details EBM for modeling the moon's surface temperatures. First, you will need to download the data from the NASA Diviner data source, as can be seen on the screen. We are going to import this data using the read CSV function, and then we are going to reshape it into a NumPy array dictated with the shape 720 by 360. Next, we are going to set up the latitude and longitude sequences using NP linspace, with our latitude ranging from -89 to +89, and our longitude ranging from -189 to +169. For this case, we are going to create a desired color sequence dictated by the colors you see in the colors array. Next, we are going to use those colors to create a color mapping sequence for our plot to use. We do need to prepare the data a bit. So first we are going to transpose the data, and then we are going to cap out our data at a max value of 400 and a min value of 100. These two lines will allow all of our data to stay within the range 0 to 400. Next, we are going to create the levels for the contour map. We are just going to take the minimum of the data and the maximum and set up a sequence of 60 between those min and max values. Then, getting to figure 5.2, which is the top panel, we are going to set up our figure using PLT figure, specifying the fig size. Then we are going to use the contour F function on our longitude by latitude with our data in there, followed by our contour levels that we are using and our desired color map. Then we are going to add some specifications to our color bar. We are going to use the contour F, CONTF, sequence to make our color bar. We are including edges, and we are specifying the specific tick marks that we want to see, 0 through 400. Next, adding the title, the X label, and the Y label, and then we are going to just add a K to the top of our color bar using the text function. This PLT grid shows the grid marks on our plot, which is important when you're looking at latitude and longitude, and then wrapping that entire block with the PLT show. We do in fact get this beautiful figure 5.2 to pop out. We can see that we have a discrete color bar over here that was handmade up in the blocks above, and this is the moon surface temperature observed by the NASA Diviner. For figure 5.2, the middle panel that you see in the book, we are going to plot the equator temperature for a single snapshot. First, we need to decide where we are looking at. So we are going to take latitude values that are less than 0.5 and latitude values that are greater than 0.5, but not exactly right at 0.5. We are going to name this data equatorial on the data sequence, which is that map matrix that we made earlier, and we will be using that specified latitude range that we were just looking at. Then on the meridian, we need to find the values that happen right on that, which is going to be everything less than 90.5 and longitude greater than 89.5. So we are only, in fact, including 1 degree in this meridian where function. Then we are going to use that where array that we get out on our data, on our map matrix that we made, to gather just the data for that meridian line. Next, we're setting up our figure. We are plotting our longitude by that equatorial variable that we got above. We are putting some nighttime text on it to dictate that this is the nighttime temperatures, followed by some daytime text, and then setting our X label to longitude, Y label to temperature in Kelvin, and setting our title. We do get this plot to show once we run this block of code. Next, in figure 5.2, this is going to be the bottom panel that you see in the book. We are plotting the noontime Myriadal temperature for the snapshot. We did make those variables in the block above, and we are just going to plot our lat1 against our meridian slice that we got from the block above, and we are making this a red line format. Set our X label, set our Y label, set the title, and then wrap that block in PLT show. And we do in fact get this beautiful plot which depicts the moon's noontime meridial temperature at snapshot 19. Next, we are going to compute the bright side average temperature. So first, we're going to go into that snapshot 19 data, which is our D19 variable, and we are going to take all of the position indexes from 129,600 to the end of the array. We are going to convert all of those numbers into a NumPy float number. Then we are going to take the cosine of those values that we just retrieved, multiplying it by pi divided by 180. Then we are making the weighted average from that BT that we computed in line 1, and we are multiplying this by the average weight. Then lastly, for our average bright side temperatures, we are going to sum up that WBT variable and divide it by the sum of our AW variable. This does in fact give us the average temperatures of the bright side of the moon, which is going to be 302.765 degrees Kelvin. Next, we can do this same process to compute the dark side average temperatures. Using the dark temperatures DT variable, we are going to grab everything before that 129 6,000 index, going up to that value, convert them into float numbers. Next, we are taking the average weight, so we are going to wrap that data in a cosine, multiply it by pi over 180, and then we are going to get our WDT variable by multiplying that DT that we defined in that first line by our AW. Next, we are going to sum up all of those WDT values and divide them by the sum of our area weighted values, which gives us the average temperature of the dark side of the moon being 99.557 degrees Kelvin. Next, we are going to use the EBM prediction for the moon surface temperature. We do have a special package that we do need to input It is from the SkyPy package. We are using the optimize function. We are naming this optimize function as OPT, so we could just use those variables directly. We do need to make a function to numerically solve the EBM. This is a EBM maker function. We do have a lot of different variables we need to use as parameters for this function. We have the definition of the function followed by the return function, which is exactly what will calculate our EBM. Next, we are actually going to use this function on some data. We're going to first set all of our variables that we are going to use. We have specified latitude, a specified sigma value, alpha value, S value, EP value, K value, H value, and a T naught value. Next, we're going to set FEBM equal to our function, which is that EBM maker, on our values. Okay. Now we are numerically going to solve the EBM for FEBM equals to 0. We do need to use that optimization package to find the root of our FEBM object on x naught equals to 400. Now we can pull out what our x naught equals using the res function, which is this variable we defined above, grabbing the x value and the 0th position gives us a EBM value of 383.6 roughly. Now going to section 5.3, which is the EBM for the global average surface temperature of an Earth with a non-linear albedo feedback. First, we need to go ahead and define our piecewise albedo function using A1, A2, T1, T2, and we are also going to create an empty array. Defining our albedo function as AB on some specified T, we're going to go into a try function. So this function in Python will try the following for loops before going into the except function. If we get a type error to pop out of this albedo try, it will default to the except portion of this definition. The only difference is that this up above function is wrapped in a for loop, wrapping through every I that's given in your T. So basically, if your T is an array, it will default to the try portion of this function. If your T value is just one value, it will default to the except portion of this function. Last thing in this block is just defining the range of temperatures we're going to be looking at from 200 to 350. Now getting into figure 5.5, we are going to plot the albedo as a nonlinear function of t. Setting up that empty array, we are going to set up our figure using PLT figure, and then we are going to plot our t function against the albedo function on that t variable. Set our y limits, set our x label, y label, and the title. Wrapping that block in a PLT show, we do get this nonlinear albedo feedback plot with albedo on our y-axis, surface temperatures on our x-axis. Now going to figure 5.6, we do have quite a lot going on in this figure. We are specifying and formulating our EBM sequence that we're looking at. We have all of these variables, A, S, EP, SG, Y1, Y2, and Y3, all predefined before going into any of our plotting figures. Now we set up our plot using PLT figure, and now we get to the lines that we are plotting. First, we plot a t variable against that y1 variable with a red line. This is going to have the label incoming energy. Next, we use that PLT plot function to plot t against y2, which is our outgoing energy. Next, we have plotted t against y2 minus y1, which is the difference between the outgoing and incoming energy. Next, specifying our y limit, we are also going to add a y equals 0 line just to see where our baseline is. And then we are going to stick a grid on our plot. Then we are going to label the title, label the x label, label the y-axis, and we are going to put some text in there to make sure our plot is as clear as possible because we do have 3 lines going on. We have labeled our E out, which is the energy out. We have labeled the energy in and also the difference between these two values. I went ahead and added some text using the roots of our difference formula. And this is our figure that we get plotted. We do have this energy out being in blue. Energy in is dictated by that red line, and then our difference line is dictated by the E out minus E in, specifying our roots of this function as T1, T2, and T3. Next, we can go ahead and verify those roots that we estimated on that plot. We're going to go ahead and set S equal to 1,365, EP equal to 0.6, SG equal to 5.67 e to the negative 8, and we're going to set up an empty array for our roots. We're going to redefine the Albedo function using a lambda variable. So we're just redefining AB as the lambda t, which is equal to 0.5 minus 0.2 times the numpy tan h, which is your inverse tan function, and we are evaluating inverse tan on t minus 265 divided by 10. Then we are going to create a function f to compute the Albedo of this function. We have another try statement using the return of the EP times SG times T to the power of 4 minus the quantity of 1 minus the Albedo on our T variable, multiplying that by S divided by 4. If we get a type error, then we are going to default to this part of the function. Next, we are using the optimization package to find the roots of the Albedo function using the bisect function on our f function on the 220 to 240 bounds. We do get a root of 234.38 roughly out of that function. Operating that same bisect function on the bounds from 275 to 295, we do get the root to pop out of 289.14. This concludes Chapter 5, Energy Balance Models in Climate. In the next video, we will start Chapter 6, which is the calculus applications to climate science.